Okay, so this is a little extra material. I said that I had an end-to-end example that I could share with folks, and a bunch of people have asked me for it, and it's going to be complicated to make that in person, so I'm just going to share it here, and then happy to answer questions about it. So so my goal here is just to show you, end to end an example that gives you some idea of how your average program reasoning tool works. And there's lots of heuristics in these tools, and in many ways all form of verification, all program verification tools are the same, but then they differ in sort of certain points where heuristics are made, and they sort of result in different user experiences or different levels of expressiveness or different performance profiles. But in some sense, in spirit, they're kind of all the same. So let's just go through it. Um, so the question, first of all, is does this program terminate? I.e., for every possible value of x and y, will we always get here? And because you're watching this on a recording, you can pause and think about it for a moment, but I'll continue on with the discussion. So the answer is that it depends on what the type of X and Y are, right? So if we're talking about in-bit integers, like 32-bit or 64-bit integers, for example, then no, it doesn't terminate. And if we're talking about unbounded integers, then it does. So let's just prove it or prove it. So the classic thing you'd see in for in particular for imperative programs, how you would verify this is there's a bit of a reduction. I'll tell you about that in a moment. That converts liveness to safety, and then safety is really induction. So typically induction, induction, you have an inductive invariant, and you check the step case, and you check the base case, and you check that the property that the invariant implies the property. And then from there, if you're using, even if you're not using an SMT solver, somewhere down deep in the engine there, it's going to be doing probably some form of contradiction and some form of abstraction, and then satisfiability. And by the way, since you're watching on this on the recording, a lot of the details here are meant to look real, but they're wrong. So don't stop and start zooming in on these and trying to understand. Well, the example I go through will be there, but this was meant more for looks, but in a talk where you couldn't stop it and to really look at it. I was planning on moving fast. So with induction, there's really three checks there. They're all kind of the same. So this kind of allows us to see the overall architecture and I'm not going through this, but if you prove temporal properties like liveness properties, that there's a couple of ways to reduce that to termination. So I have a couple. There's the sort of classic way where you reduce it to fair termination, but there's actually some work, and you can see it on my webpage about how to reduce LTL or CTL by different methods to what is ultimately a large set of termination questions. And it's actually very much like hyperproperties, actually, but I digress. So from termination, you can convert to you see often like a series of safety calls, and then from there you have a series of SMT calls, and then the SMT solver calls SAT solver. So it's this sort of Rube Goldberg machine with tools calling tools calling tools. And the termination and the liveness really handles eventually. The assert handles loops and conditionals. The SMT solver handles, plus, minus, arrays, all the sort of theory stuff, and then ands and ors are handled by the SAT solver. But what this example does not show is like recursion, concurrency, strings, these kinds of things. That's kind of where the magic is often, right? So there are ways of handling all of these ideas, but there's a whole plethora of different techniques, and I'd be happy to talk about. I know about some of them, and then others I can point you to papers. Okay, so let's go through this reduction. This actually comes from myself and my colleagues. So the idea is if we want to prove this program terminating, then we can prove this program safe. Okay, and this is for, by the way, in-bit integers. This doesn't quite work for unbounded integers, but there's a slight modification of this that handles it. So it works by introducing some new variables. So in this case, we're going to add in old x and old y, and this variable called copied. And then the idea is that the assert cannot fail is the same thing as this program guarantees termination. And yeah, as I said that, okay. So now what I can do is I can pass this program to a tool like CBMC, right? So I'm using CBMC's assert, and then I can call CBMC on it, and then it's going to say that this proof fails, and thus we can interpret that to mean that the program doesn't terminate. And so then what we can do is we can look at the counterexample, and so the counterexample is in the form of a lasso, and basically the idea is you want to go to a repeated state, right? And we can just start walking the path that the model checker gives us. And the idea is that copied is equal to 0 while we're walking through the stem, and then copied is equal to 1 when we start the repeated bit. So the idea is copied is initialized to 0. We make a non-deterministic choice at some point, and when we do, then we set copied to 1, and from that point forward, we're going to check this assert because that's protected by the copied is equal to 1. So we basically on every iteration we're asking when we're doing this non-deterministic choice, we're asking, do we want to copy the state now or not? Right. So imagine we don't, and we come back around, and again, same thing, coin toss. And let's imagine that we are. So now we're going to copy the original variables from the program, x and y, into old x, old y, set copy to 1. And from that point forward, now we're now going to get back to a repeated state because we have a counterexample here. So now on every time around this loop, now we're going to be checking this assert. Okay. And so, imagine that doesn't fail for a while, but then, now we hit it. The assert fails. So we have found a path that can be repeated forever, and thus the program doesn't terminate. Okay, so now let's talk about unbounded integers. So here what we're looking to do is to find a function f that you could pass the old state or the new state to, and you want to know that f is decreasing. So the f is on the new state is less than the old state, and the f is bound. Okay, and we have lots of choices of f. So x times y, x plus y, x minus y, 2x plus y, x to the y to the x. There's an infinite set of possible functions we could try, and this is one of these areas of magic. So the tool might ask the user for the f, in which case that makes the tool very expressive but very more difficult to use. We might find linear ranking functions using an SMT solver and Farkash lemma, in which case that it's more limited in what it can prove, but it can be fully automated. There's all kinds of techniques we could use here. And we can actually add multiple arguments here. So I could actually have 2 or 3 or 4 or any finite number of termination arguments, pieces of the termination argument. And this argument actually, this will work, right? Because we're actually checking the transitive closure. So here's the proof rule the Terminator uses, and you can read the Terminator papers to get the idea. But basically, we find lots of little termination argument parts. We combine them with union, and then because we're taking the non-reflexive transitive closure, it turns out that this allows us to show termination. Here's the R is the, I assume, is the transition relation of the program. Okay. With just one argument, we could actually do a little bit of an optimization and add exit. So with one termination argument, I can simplify this rule quite a bit and just say R is less if the transition relation of the program is a subrelation of a single termination argument, and that single termination argument is itself well founded, then we've now proved the program terminating. Okay, and I'm happy to discuss that with you further. So basically, I'm going to now substitute with f, right? So f only picks out x, so I'll just implement that here. And then the idea is that the assert cannot fail if and only if the f is a valid termination argument. Okay, and so if we pass this to a safety prover, this will pass. So we're done. So now let's talk about safety. Right? So safety is essentially induction. And so the idea is we're removing while loops, and I'm gonna sort of uh, make this point now. So now we don't care why or what the encoding where this came from, but basically we have an assert and we're trying to prove or disprove this assert. And so what we're doing is we're looking for a candidate invariant that holds at this location in the loop, right? And so I again, here's some magic, right? So some tools might ask the user for this, some tools might do some, machine learning to try and predict this. Some tools might use interpolation. There might be some trick, like IC3 style stuff. There's all kinds of tricks you can use to find this. There's just some magic that I'm applying here. And so what we're going to do is we're going to show that this invariant is established at the start, that it guarantees the assert. When this is true, then this assert can't fail, and it's maintained by the loop. And you can basically discharge all of these with SMT. So, and we can do it with what I'm calling loop-free checks, and that should become clear in a moment what that really means. So for case one, we only care where we ask, hey, when this is the checking that the invariant is established at the start of the execution. So we're basically saying, hey, if we set copy to one, we hit this conditional, we go into the loop, is this true? So we don't care about any of the code after this. So we can actually simplify that to this. And actually we can do that. So this program really represents the thing that we're trying to check. And notice there's no loops here. It's just set copy to 0, check, assume y is positive, assume x is positive, and then does this hold? And it does, because this x positive helps us here. This y positive helps us here. And because copied is equal to 0, then this disjunction is true. And so there's no loops, and thus we could actually just encode this directly into logic, no problem, right? And call that with an SMT solver. So case two, if the invariant is true, then the assert cannot fail. So this is an encoding of that problem. So I'm assuming the invariant, and then I ask, does that code from the beginning of the loop, could it fail? And it can't, because so x is positive, we know that from here, and then sure, x is 1, but then when x is 1, we know this is true, right? This is another way of saying that copied, sorry, not x is 1. When copied is equal to 1, then the x is less than old x, and thus this is established here. And note here, we know nothing of this is symbolic. We know nothing about x or copied when we come in here. All we know is what's set up with the invariant. Okay, so again, no loops, and again we can encode that to SMT. And then the third bit is the invariant maintained by the loop. And so here I've written a little loop-free program that basically establishes this. So we assume the invariant at the start, we check the invariant at the end, and we copy the loop body and the loop reentry condition in. And again, there's no loops, and again we could call SMT solver there. So now let's dig into the SMT solver, okay? So usually these work by, well, I mean, there's various ways of solving this, and we could definitely go other directions. But if you're using an SMT solver, it's by contradiction. So this is, one of our conditions from before, and we want to know that this is valid, and we can do that by adding a negation and then asking if it's unsatisfiable. So a formula is satisfiable if there are variable values that make the formula true. I imagine sort of most people here know that. But what this example is not showing is quantifiers, uninterpreted functions, strings, interpolation, nonlinear arithmetic, floating point, etc. And again, each of these features has associated solutions. I'd be happy to talk to you about how these different things work. And for some of them, I understand them quite deeply. For some, I know where to go for the information. So I'd be happy to help you out there. Okay, so what's really neat about the satisfiability formulation is there's some trick. You have this idea of equisatisfiability, and you can transform the formula in a way that's quite neat and maintain equisatisfiability. So here is the original formula, and here's a reformulation of it that's not equivalent, but it's equisatisfiable. So basically, I've applied predicate abstraction, right? For x positive, I've said, oh, x positive, let's let that be p1, and then use p1 rather than x positive, right? And so I have a Boolean only part of the formula, and then I have a convex predicate abstraction, basically, right? I'm saying, using just conjunctions of equalities, I'm assigning P1 and P2 and P3, and then I'm using them in the Boolean bit. So now there's this idea of abstraction. So we can actually just drop the arithmetic bit and use that, right? So this formula below is very, very, very finite. It's only 5 propositional variables, so there's just 2 to the 5 possible uh, cases here to consider. Whereas this is infinite, right? Because x is ranging over all integers. And there's this interesting relationship between these two formulae. So if this formula is unsat, then this formula is unsat. And so that allows us to use sat solvers on a simple logic like propositional logic to prove things that have much richer structure. Unfortunately, this correspondence doesn't hold in the other direction. So here's a quick example. So here's an unsat formula, but its abstraction is sat. So we've lost too much information. If we're trying to use this technique if we're trying to prove this formula unsat by reasoning about this one, that's not going to work. And so when abstractions fail, then the question is, do we have a refinement procedure? And we do. That's what SMT does, right? So it takes this formula, and we can infer this extra bit of information about the details here, right? So it turns out that this is an extra thing, an extra fact we can add as a consequence of this. And it's a refinement, but it's still only we're still in the language just of the propositional logic. So it's just expressed over P1, P2, and P3, and thus this doesn't make this problem any more difficult, morally speaking. And so now this formula is unsat, and thus we now know that this formula is unsat. And that's how SAT solvers, SMT solvers work. It's actually remarkably similar to SLAM, right? Where we abstract to, rather than a Boolean program like in SLAM, it's to a propositional logic. Then we ask, did we find a model? If no, then it's unsatisfiable. The overall problem is unsatisfiable, and we're done. And if yes, then we need to go into the theories. We need to handle the theories. But now it's only we're going to get a model from the propositional logic solver, so we can actually just handle the conjunctions of theory formulae, which is a lot easier. And then if that model we found is real, then we're done, and we found a satisfiable we found a model in the SMT world. And if not, then we add these conflict clauses add them into the abstraction with conjunction, and then just repeat. We can do that around and around, right? So, okay, I said all that. Great. So then now we're home free, right? So this is such a simple case, it's actually hard to explain how SAT works based on this example. So because it's not possible for P2 to be true and false at the same time, that becomes false. And you just simplify that we can eliminate that. And then P1 and P5 imply P5 and P1. And thus it's the negation of true, which is false, and thus sorry, I'll move this out of the way. And thus the whole thing is false. And sorry. So thus this formula is unsat, and the unabstracted formula is unsat, and thus the original question is valid, and thus the assert can't fail, and thus the program terminates for x and y, so long as these other two cases are also valid. And there you go. Thanks very much.